So you first have to do like the power rule and then like factor out the dy and dx. Right?
That's right. Yeah. But there's also, do you also see product rule involved there?
Oh, okay.
Mm-hmm. I'll be right back. All right, we're on page 35, and I'm going to start working number 3. Okay, so we have a equation here. We definitely have to go through power rule and product rule. to find the derivative, and we're starting with this equation, find the derivative, and then we should end up with this. We're trying to show that this is our derivative. Okay. We have to see that this is there's a need for product rule, 6x squared y. So morning. Okay, 2y cubed becomes 6y squared dy dx. Six x squared y. There's no parentheses, but these are definitely two variables being multiplied together. We have to go through a whole set of product rule there. Page 30. Six x squared becomes 12x. G is the y. Back to f. G prime, y becomes 1 dy dx. Power rule for 12x squared. 6y becomes 6 dy dx. And then the 1 goes pushed to a 0. Notice that we have 3 instances of y in the original equation, which means that we should have 3 dy dx's that show up, and we do. Now let's just clean up. Let's collect all the dy dx terms on the same side. I'm going to collect it on the left side. Factor the dy dx out. Okay, divide the parentheses over. So this is my dy dx, but their dy dx looks a little bit different. What do you think we can do to make this look more like what they want us to show?
Good morning. The new teacher meeting will take place in room 5301 at 7:45.
What do you guys think?
And factor out 6.
Yeah, let's factor out a 6. It's like GCF of 6 above and below, and that should take us down to this form. Oops, plus 1.
Say 6 and then the denominator by like 2, like another number, or do they have to be the same numbers?
They don't have to be the same number. It's just that it's easier to cancel things out if they are the same number.
Okay.
Yeah, if you factor out a 2 above and 6 below, you'll cancel out the 2, but then you're still not
Yeah.
making that numerator match. So you'll keep going. Okay, number 4. And it says find d2y over dx2. What does that notation mean? Find the what? Okay, well, what does dy dx mean? So what do you think d2y over dx2 means? Yeah, second derivative. Yeah. So we'll do one at a time. F of x equals x minus 1 over x plus 2. What rule can we use to find the first derivative? Quotient rule, yeah. All right, try that. F prime times g. Okay, we'll clean this expression up, distribute the 1 through, distribute the negative through. Okay, halfway there, first derivative. Any questions? So now to find the second derivative, we can go through quotient rule again. I think it's easier because the numerator is only a constant. We can just pull that x plus 2 to the front above, and that way just do chain rule. It feels a little bit cleaner that way, but you could definitely go through quotient rule again and get the same answer. So there's always that option of avoiding quotient rule if either the numerator or denominator is missing a variable. If it is, we can just bring everything up to the top and just rely on chain rule. So when I distribute the negative through, I get negative x plus 1. Are you getting x plus 2 minus x plus 1?
Yes.
Okay, then x minus x cancels out, then 2 plus 1 gives me 3. Let's backtrack here. Does your quotient rule look like mine? How are you getting the extra negative? Oh no, these are being multiplied. So we don't distribute unless there's another plus or minus in between. Yeah. Or if you want, you can pull the one in front of the F and just make it -1 parentheses x minus 1. So there's definitely an outside inside portion for my chain rule. Outside is my 3 parentheses to the -2. Inside is my x plus 2. Outside's derivative. Go through power rule. Keep the inside intact. Multiplied by the inside's derivative, x becomes 1. Now let's clean up. Okay, it's okay. What do you guys want to do? You guys want to do more product, quotient, chain rule, combination problems, or you want to do particle motion? We can do both. Or which you want to do first? Okay, all right. Let's do combination of product chain rule. I created these out of from a different worksheet that I did not print out for you guys, but you guys can just grab another scratch sheet. Let's try this one. All right, so our function is 3x squared times 1 minus 3x to the third, all up to the fifth. There's combination of different rules involved. You see that we have to involve if we want to find the derivative. Chain rule, okay, what else? Product rule. Which one comes first? Which one takes priority? So you look at the parentheses and you ask which rule has a larger impact on the problem. Does a product rule see more of the problem, or does chain rule see more of the problem? It could be product. The reason why is because chain rule is only impacting that parentheses, right? That's the outside inside. But product rule sees both pieces. So we have to go through a product rule first. Maybe here's an easier way to tell. If your parentheses is over the entire expression, then chain rule will come first. But if your parentheses is only over a portion of the problem, then there's the other rule that you want to apply first. So product rule comes first. And then once we're inside product rule, then we can activate chain rule. Okay, outsized derivative, 5 parentheses to the fourth. Inside derivative, negative 9x squared.
The change just doing the outside derivative and then the inside.
Yes, in a separate space. We don't put the inside derivative in here. Right. And the reason why is because the chain rule says when I take the outside derivative, I leave the inside alone. And then in a separate space, I do the inside derivative. But the tendency that students experience is that I see is they want to put this derivative in here, and it just feels like it makes more sense, right? But that's not what chain rule says. I'm not going to ask to clean up. This is a derivative that's good enough. Mm-hmm. Okay, what about number 2? What's involved there? Mm-hmm. Chain. All right. Which comes first?
Oh wait, no.
Chain. You see how chain sees more of the problem than quotient does? Yeah. Okay, so start with chain. And once you're inside chain, then quotient rule will take effect. Outside derivative, we do power rule. Fill the inside with the original expression. Multiply then by quotient rule. We can put all this under one fraction.
We would just add the denominator.
Mm-hmm. Yeah, why is that a 6? Yeah, that 4 is impacting that below as well. There's 4 of these, 4 of the x minus 5x to the 4th. There's 2 of them here. Add those together to get 6. Back to page 36. We can do a particle motion problem there. Position of the particle traveling along the straight line is x of t in terms of t. T is greater than or equal to 0. Let's go ahead and find our velocity and our acceleration functions. And we can also create our velocity sign line as well. Okay, I'm choosing to test numbers in each subinterval so I can know the direction of movement for each of these subintervals. Plug 1/2 into my velocity function. 1/2 minus 5 is negative. 1/2 minus 1 is also negative. 2 negatives makes positive. Plug 2 in. Negative times positive is negative. Plug 6 in. Positive times positive is positive. So it says when is particle moving to the left? Moving to the left is negative direction. So moving left on the interval from 1 to 5. Right? Is speed increasing or decreasing? We have to check the signs, right? We know v of 2 is negative. We know a of 2 plug 2 into the acceleration. I'm going to get a positive value, 24 minus 18. So if one is positive, the other is negative, I know speed is going to be, wait, let's see, v of 2, a of 2. Oh, I messed up. 6t minus 18, not 6t squared. I forgot to drop that exponent by 1. So 2 into acceleration, 12 minus 18, that's negative. So now we have same signs. Same signs means speed is increasing. Okay, average acceleration. Remember how average velocity uses the function above it, change in position over change in time? Average acceleration, also, we don't use acceleration. We use the function above it. We use velocity. So we find change in, we define average acceleration as the change in velocity divided by the change in time. Okay, where's the particle located when the velocity is 0? We know velocity is 0 at 1 and 5. We found that earlier. So we just plug 1 and 5 into the position function to find the location. Okay. You use your calculators, plug 1 and 5 into the position function to find the locations. Okay, displacement. Displacement is defined as final position minus initial position. So we just do x of 3 minus x of 0, and that's it. Sorry?
Do you want me to close the door?
Yeah, great, thanks. X sub 3 is -6. X sub 0 is negative is 3. So -6 minus 3 is negative. And now distance it's kind of like displacement, but we have to see, is there a change in direction that this particle is experiencing? So we know x of 0 and x of 3 are both involved. But between 0 and 3, we do see this object changing direction, so we have to backtrack, right? So we only, between our endpoints, we only care if there's any locations of change in where the particle changes direction. And then we're going to find those locations, and we're just going to imagine ourselves walking between those markers or x values, and then counting our steps as we walk. Okay, so all this is plugged into the original function. So now imagine yourself walking from 3 to 10, and then back to -6. So from 3 to 10, how many steps would you take? 7. From 10 to -6, how many steps would you take? 16. How many steps have you taken in total? 23. That's your distance. Okay, we'll do some more particle motion in class today. Right?